Decollage liftoff from a tropical rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe. There's your telescope, and begin its journey to the Lagrange point, the L2 point, about 1 million miles away from Earth.
Imagine standing on a quiet hill, staring into a clear night sky. Thousands of stars twinkle above you, calm, distant, eternal. Now, imagine being able to see beyond them, not just through space, but through time itself. Back to a moment when stars had just begun to shine, when galaxies were infants, when the entire universe was barely 300 million years old. Thanks to the James Webb Space Telescope, we're no longer imagining it, we're witnessing it. Webb's golden mirrors have captured light older than Earth itself, revealing galaxies no human has ever seen until now. Galaxies that shouldn't even exist yet. Too massive, too fast, appearing far earlier than our theories allow. It's as if the universe is breaking its own rules, and we're left asking, what else have we misunderstood? About everything. This is not just about stars, this is about the origin of time, of us, of everything, and it begins with a telescope floating 1 million miles from Earth. Imagine standing on that quiet hill again, but now you're holding a mirror in your hand, reflecting not yourself, but the light from galaxies formed over 13 billion years ago. That's exactly what NASA's James Webb Space Telescope, JWST, is doing, capturing ancient light to probe the universe's earliest moments. Launched in December 2021 and parked 1.5 million kilometers from Earth, the JWST unfolded like a giant origami masterpiece, an infrared eye wrapped in a sunshade the size of a tennis court. That sunshield blocks the warming glare of the sun, Earth and Moon, giving Webb an SPF of 1 million, letting it peer deeper into space than any previous observatory. But what really sets it apart? Its infrared mirror beams can travel through cosmic dust and across eons, collecting photons that have drifted since the universe was less than 1 billion years old. In July 2022, Webb's first deep field images stunned us all at once, revealing galaxies from the cosmic dark ages when the universe's first lights flickered on. One image from NASA's archive shows distant galaxies appearing as faint golden smudges, flavors of the early universe no Hubble could detect. Another snapshot, part of the JWST project, displayed JWST GSZ 14-0, a galaxy so distant its light began its journey just 300 million years after the Big Bang. Even more bizarre, 6 galaxies observed in Webb data appear vastly too massive and bright for their age, some as massive as the Milky Way, despite forming at cosmic dawn. Astronomers jokingly call them pool noodle galaxies, flattened shapes unlike anything we see today. They're morphology freaks existing models. 50 to 80% of early galaxies appear stretched like cosmic surfboards or noodles. And the surprises don't stop there. JWST is identifying candidate galaxies with redshifts over 14, light that started when the universe was a toddler, under 300 million years old. One name making headlines is MOM Z14, the farthest confirmed galaxy at Z equals 14.44, dating a mere 280 million years after cosmic birth. This extraordinary reach is redefining our cosmic timeline. What was once impossible, massive galaxies this early, is now staring us in the face. JWST is rewriting chapters in astronomy textbooks overnight. Next up, we'll dive into the biggest mystery of all, why these galaxies seem to break the rules of formation and what it could mean for our understanding of everything. Picture a universe still in its cosmic toddler years, just 600 million years after the Big Bang. You'd expect baby galaxies, small, fuzzy, round blobs forming slowly. Instead, the James Webb Telescope shows us something wild. Most of these early galaxies aren't blobs at all. They're stretched out surfboards and pool noodles. In a deep field survey, SEERS, Webb found that about 50 to 80% of galaxies in the early universe are flattened and elongated, like cosmic surfboards. Closer to home, that shape is super rare. Our Milky Way? Round. But back then? Not so much. These shapes tell a story. Early galaxies likely formed along the filaments of the cosmic web, merging and stretching into long, thin shapes instead of spinning into disks like modern spirals. It's like watching a beach party of galaxies, not in neat rolls of cosmic dough, but long, wild waves. Then there's the mass problem. Take MOM Z14, the farthest confirmed galaxy yet. Light from this relic travelled for 13.53 billion years, placing it just 280 million years after the Big Bang. And it's not a tiny smudge. It shines with constant star formation, has nitrogen and carbon, and is surprisingly compact at just 240 light-years across, with a stellar mass similar to the Small Magellanic Cloud. This galaxy alone challenges our cosmic timeline. How did it grow so massive so fast before heavy elements even had time to form? It gets even more puzzling. Just a year ago, Webb detected JWST Z14-0, another ancient giant, just 290 million years post-Big Bang, with a mass of around 500 million suns and surprising luminosity. Even more astonishing, it contains oxygen, a heavy element thought impossible so early. Again, massive, luminous, and chemically evolved. That's not evolution, that's cosmic fast forward. Early galaxies seem to be sprinting through cosmic development, collapsing and forming stars at breakneck pace, packing heavy elements like nitrogen and oxygen far too soon. But what does this mean for our galaxy formation models? Our standard theories, hierarchical build-up in dark matter halos, slow gas inflow, gradual evolution, don't accommodate these cosmic toddlers existing as giants. Some explanations being explored include clumpy cold gas inflows, fueling rapid star formation, early feedback mechanisms, making star formation more efficient, or even the possibility that our basic assumptions about dark matter need revision. These oversized toddlers are telling us something critical. The early universe might be more dynamic and unpredictable than we thought. So what's next? Tomorrow's telescopes, the Nancy Grace Roman Space Telescope and future JWST spectroscopic campaigns will probe whether these are cosmic outliers or the norm. They'll dive deeper, spectrally and spatially, to tell us how these galaxies build heavy elements, form stars, and evolve in ways we've never expected. For now, we stare into the cosmos and realize the universe is full of surprises. What it all means for our origin story, why early galaxies rewriting physics changes how we see ourselves in the grand cosmic timeline. Imagine rewriting the cosmic rulebook. That's where we're standing today. JWST has shown us early galaxies so massive, so bright, that they seem to contradict our core cosmological model, lambda CDM. But here's the twist. The crisis might not be as severe as it first appeared. Those early galaxy giants. At first glance, they felt like a crisis. Bright, ultra-massive galaxies where none should exist, bathed in intense star formation, 1,000 times the Milky Way's rate in teeny cosmic timeframes. Models based on lambda CDM didn't expect galaxies so dense and chemically rich so early. For example, JWST Z14-0 had oxygen and other heavy elements just 290 million years post-Big Bang. At first, alarm bells rang. But new research shows the picture is less grim. Image calibration, simulation refinement, and acknowledging burstiness in star formation brought many observations back into alignment. The outer cosmos may simply look different at the dawn, denser, dynamic, efficient, JWST is now rewriting, not breaking, astrophysical rules. One key idea: black holes are playing a role. Massive black holes in early galaxies may accelerate structure growth or create brighter appearances by intensifying star formation or feeding off gas. A few skeptics even suggested more radical fixes like tired light models or early dark energy to push back cosmic timelines and give galaxies extra time to grow. But such ideas clash with the bulk of data: cosmic microwave background, supernovae distances, and expansion history resist such drastic tweaks. Today, most cosmologists see a clearer path. Better JWST calibration reduces overestimates in mass and brightness. Complex starburst activity explains ultra-bright early galaxies without invoking new physics. Black hole and gas feedback may lead to faster than expected galaxy buildup. Bottom line: the standard cosmological framework still holds, but now with richer, more dynamic early history. JWST hasn't overturned cosmology. It's revealed its vivid undercurrents. This isn't just astrophysics, it's a cosmic mirror. These revelations tell us how stars, atoms, and ultimately planets formed, including our own. Seeing oxygen, carbon, and nitrogen so early underscores that the raw materials for life were stacking up far sooner than we guessed. The universe may have been fertile earlier than assumed. The next generation of telescopes, like the Nancy Grace Roman Space Telescope and deeper JWST spectral surveys, will push past 14+ billion years ago, hunting even more ancient galaxies. As we refine our cosmic timeline, something becomes clear. The universe might have been smart and fertile from day one. The James Webb Space Telescope hasn't just changed how we see the universe, it's changed what we believe is possible. In a cosmos once thought simple and slow to evolve, we've found speed, chaos, and brilliance beyond imagination. And as we uncover these ancient lights, we're reminded that the story of the universe is far from over. It's only just begun.